In the previous section, we described resources for integrating third-party intellectual property. By the end of this module, you will be able to describe a few examples of parallel loops executing on FPGA. In Lesson 8, we're going to discuss sharing data on FPGA. So to start off, we're going to talk about parallel loops on FPGA. Then we're going to talk about shared resources, and then we're going to talk about how we can share latest data between FPGA loops. Then we'll talk about how to transfer buffered data, and then lastly, we'll just do a comparison of the data sharing methods that we discussed in this lesson. So on this slide, we see that there's some parallel execution here. So notice that with the parallel execution, which we've talked about before, it's implemented in parallel on the hardware on the FPGA chip. So using LabVIEW FPGA, since it's a graphical programming language, it's very easy to create parallel code and visualize it. So on this slide, notice that we've got two different loops. By using two different loops, we can very easily implement two different sampling rates. So if we look at the top loop, we've got that running with a certain period. So if we look at the loop timer, we're defining the period with that control slow period. And then at the bottom there, we've got another loop that's running in parallel, and we can have that loop running at a very fast period. That's determined there by the loop timer with the fast period control. So let's talk about the loop rate limitation real quick. The loop rate is going to be determined by the longest path that's in that loop. So if we're taking a look at this particular example, this example is going to take about 38 ticks to execute. And the reason why is if you look in there, there is an FPGA I/O node. So what's taking the longest time there? Notice that we've got an analog output terminal there, and that analog output terminal is going to take about 38 ticks. If we look at the digital one, however, that terminal writing to a digital output, or in this case reading from a digital input, is going to only take 1 tick. So notice that this whole loop is being limited by the 38 ticks of the analog output. So let's see what we can do about that. So notice over here in this slide, what we've done is we've separated the analog output from the digital input. So now the analog output loop that we see at the top is taking about 38 ticks to run. And if we take a look at that bottom loop, because it's in a separate loop, the digital loop is able to run much faster. It's only going to take 4 ticks. So in the previous examples that we just looked at, there was no data dependencies between those two loops, so they were able to run completely in parallel and had nothing to do with each other. However, what if you want to pass data from one loop to another loop? Since the loops are running in parallel, you can't use a wire to pass that data. You need to be able to use something that can be shared among multiple loops, and that's what we'll talk about in the remainder of this lesson. Now you can describe a few examples of parallel loops executing on FPGA. Next, we will describe and list shared resources on FPGA. In the previous section, we described a few examples of parallel loops executing on FPGA. By the end of this module, you will be able to describe and list shared resources on FPGA. In this section, we'll talk about shared resources. So what is a shared resource? It is any resource that is accessed by multiple objects in an FPGA VI. So here we list a couple examples of shared resources. So digital outputs on most targets, analog inputs, analog outputs, digital inputs, non-reentrant sub-VIs, also memory items, registers, and FIFOs, which we'll talk about later on in this lesson. So these are all resources that can be accessed in parallel loops. So let's talk about shared resources a little bit more. Before a task can begin using a shared resource, though, it must wait until the resource is free. So let's take a look at this graphic right here. So let's look at the top graphic. Let's say we've got a shared resource, which is there in the middle, and we've got task 1 that's running and also task 2 that's running. And both of those tasks need to access that shared resource. So let's say task 1, so let's say loop 1 is running and it's using that shared resource. Well, while task 1 is running and using that shared resource, task 2 is sitting there waiting on that resource to be available. So let's say task 1 finishes. Now after task 1 finishes, task 2 can proceed. So if we look at the bottom now, task 1 is just finished, so now task 2 can now use the shared resource. So in the meantime, while task 2 is using the shared resource, task 1 will have to wait if it's trying to use it again. Using shared resources causes jitter within the application. To maximize the determinism of our VI, we need to try to avoid shared resources when we can. So let's take a look at this slide. Can you identify where the shared resources are in this slide? So notice we've got a loop at the top and a loop at the bottom. So there are two shared resources here. So one of the shared resources is the analog input channel. So notice that both of those loops are accessing analog input channel 0, and the other shared resource is analog output 0. So because both loops are trying to access these resources, they're going to have to wait on each other because only one loop can access that resource at a time. Now you can describe and list shared resources on FPGA. Next, we will share latest data between parallel loops running in the same FPGA VI using local variables and share latest data between multiple FPGA VIs using global variables. In the previous section, we described and listed shared resources on FPGA. By the end of this module, you will be able to share latest data between parallel loops running in the same FPGA VI using local variables and share latest data between multiple FPGA VIs using global variables. Okay, so let's talk about sharing latest data. So if all you're wanting to do is share the latest data between multiple loops, what you can do is you can use one of these methods. You can use local and global variables, memory items, or register items. So in this particular module, we'll talk about local and global variables. So variables are block diagram elements that allow you to access and store data in the flip-flops of the FPGA. So by now, if you've come from using regular LabVIEW, you should already know local variables and global variables. But just know that when you use these on FPGA, it stores that actual data in flip-flops. So this is a good method to use if you're wanting to store only the latest data that you write to it. So if you need all historical values or buffered values, this is not a good method. This is only going to share the latest data or the most current data that you've written to it. So there's two types of variables that we're going to talk about on FPGA. One is going to be local, which is accessible only by a single VI, and there's also global variables, and those will be accessible by any VI that's running on the FPGA target. So local variables, they're going to store the data that's in front panel controls and indicators. So if you look at the bottom there, there's a stop button. If I wanted to share the value of that stop button within that VI, I could use a local variable for it, which you see right there. So on the right-hand side, you see the stop local variable. Local variables are only accessible within a single VI. You can also use them to maintain data separately for separate reentrant VIs or separate reentrant sub-VIs. The way that you can create a local variable is you can right-click on any controller indicator and you can select Create Local Variable, and then that will allow you to create that and place it on your block diagram. If you're using this approach, so if you're using local variables just to be able to share data between loops, you might find yourself creating controls and indicators only for data sharing within the VI that they're on. So if you're doing that, you might want to create a coding convention to help you distinguish which controls and indicators are used for simply data sharing and which ones are used for passing data in and out of the VIs. So if you're doing this, you might want to use global variables instead also, if you're only using a local variable and a control just for passing data. So here we see a local variable example. So here we have two parallel loops, loop 1 and loop 2, and the data that we're trying to share in this case is the value of the loop control. So if we look at loop 1, we have the loop control boolean right there, and in loop 2, we've created a local variable to read the value of the loop control, and that way we're able to stop both of the loops at the same time. Now let's talk about global variables. So global variables are also able to share the latest data. However, they are accessible through multiple FPGA VIs instead of just a single one. The way that you would create a global variable is you would go to the functions palette and you would select structures global variable. Previously, if you were creating a controller indicator only to use the local variable for data sharing and you actually weren't really using that controller indicator, you can consider replacing that with a global variable instead, and that way you'll decrease FPGA resource usage because you don't have to implement that FPGA code that was just trying to pass data between the FPGA and host. Now you can share latest data between parallel loops running in the same FPGA VI using local variables, and share latest data between multiple FPGA VIs using global variables. Next, we will share latest data between multiple FPGA loops and VIs using memory items. In the previous section, we shared latest data between multiple FPGA loops and VIs using memory items. By the end of this module, you will be able to share latest data between multiple FPGA loops and VIs using register items. So another method we can use to share latest data is register items. So register items are very similar to memory items, and we'll talk about a couple of the differences in this section. The similarities, just like memory items, register items are only going to share the most recent data. And also like memory items, you can have target scope register items and VI defined register items. So the way that you would create these is going to be very similar to what you did with memory items. So if you look at the target scoped side, so on the left-hand side, the way that you would create one of those is you would right-click your FPGA project, go to New, and then choose Register, and then you would go through a configuration window to configure that. And then again, on the right-hand side, for a VI-defined one, if you only want that register to be able to be accessed within one VI, you can create it in a similar way. You would go to the programming palette and then the data storage and transfer palette, and then you would select VI defined register instead. Okay, so very similar so far to memory items. So again, similar to memory items, with a register item, if you're looking at the configuration window, you can initialize its value. So notice that for our register item, there's not a whole block of elements that you can store inside a register item. So with the memory item, remember you can store several addresses of different values. In this case, a register item is only going to store one value. So you can go to the properties window here, and if you select the initial value category on the right-hand side, you'll see that you can either manually specify the initial value in that box over there, or you can also use a initialization VI that you create to do some custom initialization for that initial value. So here are a couple differences between register items and memory items. Register items access or store data in the registers of the FPGA. Okay, so it's a different implementation in the hardware. Register items do not consume block memory, which is the most limited type of FPGA resource. Also, register items only share one element, and that's different from memory items. Like I said earlier, a memory item can share a block of elements. With a register item, you can only share one element. And the other difference is, with a register item, you can share data across multiple clock domains safely. Okay, so if you're trying to go between two single cycle time loops that are running at different clocks, for example, you can share data between those two safely using a register item. Now you can share latest data between multiple FPGA loops and VIs using register items. Next, we will avoid race conditions when sharing latest data. In the previous section, we avoided race conditions when sharing latest data. By the end of this module, you will be able to transfer buffered data using FPGA FIFOs. Okay, so now we're going to switch gears a little bit. Right before this, we were talking about different methods of sharing latest data. Now let's say you want to transfer buffer data. So in this case, you want to transfer every value from one loop into the next loop, or from one VI to the next VI. So if you want to transfer buffer data, you'd want to use something called FPGA FIFOs. So what is a FIFO? A FIFO stands for first in, first out buffer. The first data item written to the FIFO is the first item that's going to be read and removed from the FIFO. So this is similar to queues in LabVIEW. So with a FPGA FIFO, you can create one that's target scoped, or you can create one that's VI defined. Again, if you're creating a target scoped one, that FIFO is going to be able to be used between loops on multiple VIs running on the same FPGA target. If it's a VI defined FIFO, then that single FIFO will be able to transfer data between multiple loops in the same VI. So first, let's talk about how to create a target scoped FIFO. So the way that you would do that is you would right-click an FPGA target, you would go to New, and then select FIFO. Okay, and that'll launch a configuration window for your FIFO. So if we take a look at this dialog box, we notice that we can give our FIFO a name, and that's the name that'll show up in the project. And also I want to bring your attention to requested number of elements. So this is how many elements that you're going to store inside your FIFO. Okay, and then we'll talk about the implementation as well. So in this case, it's shown as block memory, but there are other ways that you can set that. So you can either use block memory, lookup table, or flip-flops, and we'll talk about that in a later slide as well. So let's talk about that number of elements setting on that previous configuration window we just saw. So the maximum is going to depend on the implementation that has been selected, which we'll talk about in the next slide, and also on the amount of space available on the FPGA for the implementation. So if you specify a value that is too large here, the FPGA will fail to compile. Also, you want to request the number of elements based on the needs of your application. So just try to think of, okay, how much space do I need in that FIFO? LabVIEW is going to specify the actual number of elements in that window, and if the actual number is greater than the requested number, the difference is due to technical constraints on the way that it's implemented on the actual FPGA hardware. So on this slide, we're talking about that implementation setting on the configuration window for the FIFO. So there are three types of implementations that you can choose from. One is flip-flops, one is lookup table, and the last one is block memory. So on this slide, we kind of provide you some best practices of which one you should choose. So let's talk about flip-flops. This implementation will use gates on the FPGA to provide the fastest performance. However, this is only recommended for very small FIFOs. So if your FIFO is less than 100 bytes, then you can use flip-flops. Now, if your FIFO is going to be a little bit bigger, then you might want to use lookup tables instead. So this implementation will store data, the data of your FIFO in lookup tables available on the FPGA. This is recommended for small FIFOs that are between 100 and 300 bytes. Lastly, there's block memory. So for block memory, this stores your FIFO data in block memory to preserve the FPGA gates and LUTs for your VI. So this is recommended for FIFOs that are going to be greater than 300 bytes. So here we see that you can also create a VI-defined FIFO. So again, a VI-defined FIFO is going to be a FIFO that you can only use between different loops on the same VI. You would go to the data storage and transfer palette, and you would place down a VI-defined FIFO, and then you can double-click it, or you can right-click and select Configure to launch the properties to configure that FIFO. Okay, so now let's talk about how to write and read from your FIFOs on your block diagram. So what you would do is you would place a FIFO method from your functions palette and place it on the block diagram. From there, you could right-click it and then go to Select FIFO, and then select the FIFO that you've defined already, that you want to associate that write and read with. Then you can right-click the object, select Method, and choose Write or Read, depending on whether you want to write or read. Another way you can do it is you can left-click on top of where it says Write on the actual node and change it to Read, or change it from Read to Write. Okay, let's take a look at the FPGA write and read nodes a little bit more closely. So once you have them up, notice that there's going to be an input or output for element. Okay, so this is going to be where you would either write an element or you would read an element from the FIFO. There's also a timeout. So if you take a look at that, let's look at the one on the left first. So let's look at the FIFO write. So let's say I have an element that I'm trying to write to my FIFO, and then I have a timeout specified there. So if I'm trying to write an element to my FIFO and the FIFO happens to be full already, then it's going to wait for the time that's specified by the timeout. And if there's no space still at the end of the timeout, then the timed out output will be true. Okay, and that would indicate a overflow condition, which we'll talk about more on the next module. Now let's take a look at the FPGA read on the right-hand side. So here we have an element that we're trying to read from the FIFO, and we also have a timeout here. So if we call this read and the FIFO happens to be empty, then this node is going to sit there and wait until there's an element available. Now if the timeout specified times out, then the timed out will output a true, and that would indicate a underflow condition, which is what we'll talk about in the next module as well. Now let's go into LabVIEW and take a look at the FPGA FIFO. So in this demo, what I'm going to do is I'm going to create a target scoped FPGA FIFO item. So here we will go to our FPGA target and right click it, go to New, and then select FIFO. And in this case, I'm just going to call it My FIFO, and that's what the name of it will be in the project. And then here I want it to be target scoped, and here I can define how many elements I want this FIFO to contain. So in this case, I'm just going to leave it at 1023. Here, notice that you can select the implementation. So we talked about this in the previous slides of what's going to be the most optimal for you. So here, I'm just going to leave it on block memory. Notice that you can also go to data type, and you can also select what kind of data you want your FIFO to contain. So here, I'm just going to leave it at I16, but notice you can choose other data types as well. So I'm just going to click OK. And notice that I have my FIFO right here. Now I'm going to right click and create a VI so we can go to the block diagram and write or read to it. So if I right click, I can go to data storage, then I can go to FIFO method. I can place that down, and notice I have to say what FIFO this is associated with. So I can right click this, select FIFO, and select my FIFO. Okay. I can also go over here and drag it from my project into my block diagram. So either way, I can do a write, or I can left click here and change it to read. Okay. So this is how I would write to my FIFO or read from my FIFO. Okay, and notice that here, this is the element that I would write, this is the element that I would read, and here we can specify a timeout just in case the FIFO is full when I'm trying to write to it, and here I can specify a timeout in case the FIFO is empty when I try to read from it. Now you can transfer buffer data using FPGA FIFOs. Next, we will handle FPGA FIFO overflow and underflow conditions. In the previous section, we transferred buffer data using FPGA FIFOs. By the end of this module, you will be able to handle FPGA FIFO overflow and underflow conditions and describe the behavior of an FPGA FIFO. Okay, so now let's talk about FIFO overflow and underflow. We kind of mentioned it in the previous module. Let's talk about it a little bit more now. So an overflow condition, this happens when the writing loop executes faster than the reading loop. So what would happen is when you're trying to do a write to that FIFO, the FIFO is already filled up and the FIFO write method will time out. So when this happens, data is not written to the FIFO until there's space available. Okay, and the only way that you can have space free up in a FIFO that's full is, one, you can read an element out of that FIFO, which creates space for another one to put in, or you can reset that FIFO. So if the FIFO remains full and you keep trying to write to it, at that point you're losing that data that's happening. So because you're losing data, that's why it's important to know when you're overflowing. Now let's talk about underflow. So underflow happens when the write loop is executing slower than the read loop. So in other words, the read loop is executing faster, and then at that point the FIFO read will try to read from the FIFO, but there's no elements there to read yet. Okay, so the FIFO is empty, and then when the FIFO read tries to read from it and it times out, then that would indicate a underflow. So how would you handle FIFO overflow or underflow? So the method for handling this would depend on the importance of lossless transfer. So if you do care about making sure that every piece of data is transferred from the writer to the reader, then you would want to monitor the overflow. So let's take a look at this block diagram. Okay, so we have a FPGA I/O node, and then we're using that value, and we're going to write that value into our FIFO. So if we take a look at our write method, we're writing that element to the FIFO, and then we have a timeout of 0. So what that means is when it gets to this write method, it's going to check and see if the FIFO is full. And if the FIFO is full, because the timeout is 0, it's not going to wait at all. It's just going to immediately time out. Okay, and timed out will equal true. So let's say the FIFO is not full yet. Okay, and we're running this loop and we keep writing. Well, if the FIFO still has space, then we're still good to go, okay? And everything is operating as normal. However, if the FIFO fills up, and then we try to write to it with this write method, then it's going to time out, right? Because if the FIFO is full, we can't write, there's no space for us to write a new element into the FIFO. At that point, timed out is going to output a true value. So overflow, that indicator will now be true. And at the same time, we see that it branches down and it also stops the loop. So as soon as that overflow condition occurs in this particular VI, we can be alerted that there's an overflow that occurred, and we're also stopping the VI because we know that we're getting some data loss and we need to go fix something, okay? And the data has been compromised. So another way that you can handle this is if you wanted that while loop to keep running, for instance, instead of stopping the loop, what you could do is you could look at the timed out output, and you can latch it using either a shift register, or you can use a feedback node, and you can just have something that tells you if the loop ever had a overflow condition. Okay, so in this next portion, we're going to do a demonstration, and we're going to take a look at how FIFO works with writing and reading, and how many elements are in the FIFO, and we'll take a look at overflow and underflow as well. Okay, so let's take a look at this demo. So if you want to follow along or play with this later, you can find the same VI in the exercises folder in the demonstrations folder. So let's take a look at this VI. I'm going to go ahead and run this. And let me talk about a couple things. If I hit write, we're going to start writing to our FIFO, and if I hit read, we're going to start reading from the FIFO. Okay? So this bucket that we see here, we have a FIFO, and the size of that FIFO is going to be 36 elements. Okay? So this bucket here is going to show us how many elements are currently being used in the FIFO. Okay? So let's go ahead and hit write. Notice that I'm writing, and because I'm not reading, the FIFO is starting to fill up. Now if I was to read, notice that I'm writing and reading at the same rate for this particular example, and because that's happening, the FIFO is just remaining at 25. Okay? Now if I stopped writing and I kept reading, what do you think would happen? Well, let's see. If I stop writing, but I keep reading, then I should start emptying the FIFO, right? So let's see what happens if I keep reading. So notice that the FIFO underflow is turning on right now. The reason why is because I'm trying to read, but there's nothing to read in the FIFO. Okay? So underflow conditions usually aren't that bad. I mean, if you're trying to read and there's nothing in the FIFO, and it underflows, then that's not too much of a problem. You just keep trying to read again until something appears in the FIFO. Okay? So I'm going to stop that. And I'm going to start writing again. So let's see what happens if I keep writing and the FIFO fills up and I still keep on writing. So notice it's starting to get full. Now my write method, now I'm trying to write, so I'm trying to write some new data, but I can't write anything because the FIFO is already full. It's already been filled up to its size of 36 elements. Okay? So notice that on the write method, if I time out on that, then the timeout is going to equal true, and that's going to indicate a FIFO overflow. Okay? So a FIFO overflow is going to be bad, because a FIFO overflow means I'm trying to write some data right now, but it's being lost because I don't have any room in the FIFO to store it. So hopefully now you have a better understanding of how writes and reads affect the FIFO, and what a FIFO overflow represents, and what a FIFO underflow represents. In the previous section, we handled FPGA FIFO overflow and underflow conditions. By the end of this module, you will be able to use FPGA FIFO methods to get number of elements and clear the FIFO. So on this slide, we see two additional methods that you can access using the FIFO method node. So first, let's talk about get number of elements to read. This one's going to return the number of elements remaining in your FIFO to be read. You can also use the get number of elements to write instead, and this one will return the number of empty elements remaining in the FIFO. So both of these are just two different ways of getting similar information, and you can use these methods to avoid underflow or overflow conditions by monitoring the status of the FIFO. So if you know how many elements are in that FIFO, you can maybe take some action to, if it's getting near overflow, maybe you can address that somehow. Okay, so one thing I want to bring up about FIFOs. So FIFOs retain data if the FPGA is stopped and restarted. Okay, so between stops and restarts, that FIFO is still going to retain its data. So usually that's not the behavior you want. Usually you want to start off with a empty FIFO when you're starting your FPGA VI. So if this is the case, then it would be good for you to use the clear method inside your FPGA VI. Okay, so when you use the clear method, it'll automatically or programmatically clear that FIFO. The way that you would get to the clear method is you would place down a FIFO method node, and then you can right click on it and then select method, control, and then clear. Okay, so at this point, if you're able to, go ahead and do exercise 8.1. And in this exercise, we will try to create an accelerometer threshold. And the way that we're going to do that is we're going to use some FIFOs and a lot of other different components. So for now, let me just demo the solution to you, and you can take a look at it. Okay, so I've opened up the solution for exercise 8.1. And if we look here, we've got a CRIO that we're connected to right now, and we're going to create an FPGA VI for it. Okay, so one of the first things we do in this exercise is we create a target scope FIFO. In this case, we called it Y acceleration FIFO. and we're going to use this in our application. So now the FPGA VI is called accelerometer VI, which is right over here. So let's take a look at it. Okay, so let's go to the block diagram. So let's break this down real quick. So in the very first sequence, the first frame of the sequence structure, we're doing some initialization. So here we're setting some things to false. We're starting our module. We're specifying the data rate for our 9234 module. And then also notice here we're doing a FIFO clear. So because we expect that the FIFO is going to be clear at the beginning of this program, we're going to explicitly call the FIFO clear function to ensure that. Okay, now let's jump into the main code. So here we have an acquisition loop, and in the acquisition loop, what we're doing is we're reading the Y acceleration of a fan through a FPGA I/O node. Okay, the next thing we're going to do is we're going to take that data and we're going to write it to our FIFO. Okay, so we're putting that into the FIFO and we're going to read it out in the loop right underneath it. Okay, so we're going to write some data to the FIFO. We're also going to look at the timed out and monitor it and see if overflow occurred. If we happen to get an overflow, we're going to go ahead and stop our application and terminate it. Okay? So let's look at this bottom loop. So in the processing loop, we're going to read data out from our FIFO. Okay? So this has been transferred to the FIFO up here, and down here we're going to read elements from it. And notice that we're going to look at the timed out. So if this times out, that means the FIFO was empty. So if timed out equals true, we're just going to do nothing. Okay? However, if we read from the FIFO and it doesn't time out, that means we were able to grab some data from the FIFO. And in that case, we're going to take that data from element and we are going to display it on a indicator. And also we're going to do some processing with it. We're going to compare the current acceleration with the acceleration threshold. Okay? And if we see that the acceleration threshold is been exceeded by our acceleration, then we're going to display threshold exceeded as an indicator, and we're also going to write something to an FPGA LED. Okay? And then also we're going to monitor the terminate from up here, and if this has been terminated, then we're also going to terminate this loop down here. Okay? Lastly, we have a third loop here, and this is a loop that's controlling the speed of our fan. Okay, so here we have a fan speed control. Depending on how high that is, that's how fast our fan is going to be spinning. Okay, and we're also going to monitor the terminate control here as well. And then lastly, if we terminate, what we're going to do is we're going to make sure that we stop our FPGA I/O node, and we're also going to reset the fan speed to 0. So if something bad happens, we're just going to make the fan stop by setting it 0. Okay, so let's take a look at our front panel, and this has been compiled already. So I'm going to run this real quick. Notice that we're monitoring the acceleration of our fan, and right now we have a threshold here. So if it crosses this threshold, we want to know about it. Okay, the data rate we're going to acquire at is right over here. So let's start increasing the fan speed and see what happens. So it looks like, oh, well, now the threshold is starting to get exceeded. And if we keep making it higher, notice that the acceleration keeps getting exceeded. Okay? So it looks like our application is working. And looks like things are going pretty good because no overflow has occurred. And yeah, you just want to make sure you always monitor your overflow just so you know if you're missing some data possibly. So it looks like we are not missing any data here, and the program is running as expected. Okay, let's talk about some discussion questions. So why is it important to configure the FIFO data type to match the data that you will be writing to it? So this is important. You want to make sure that when you configure your FIFO, whatever data you're writing into it, you want it to match. Otherwise, there might be some coercion dots and you might have some unexpected behavior and it won't be as efficient. So in this case, the data type that we were putting into the FIFO was coming from our 9234 module. So what we should have done is we should look at the wire that's coming out of that particular module and see what the fixed point representation is. And when we create our FIFO, our target scope FIFO in the project, we want to make sure we make it a fixed point data type with the exact same configuration. Okay, so with the exact same sign encoding, word length, and integer word length. Second question, could this application have been developed using a VI-defined FIFO? In this case, yes. The reason why is because the FIFO is being only used on a single VI. So in that case, a VI-defined FIFO would have been fine. However, if we wanted to use sub-VIs to handle some of our FIFO functions, then we must use a target scope FIFO because that FIFO would have been shared between multiple VIs, namely the main VI or between sub-VIs. What is the purpose of the FIFO clear method in this exercise? So notice that in the very first frame we had a FIFO clear, and the reason we did that is because FIFOs will retain data between runs. In this case, for this application, we want to make sure that the FIFO is clear when we first start, so that's why we put a FIFO clear in that very first frame. Now you can use FPGA FIFO methods to get number of elements and clear the FIFO. Next, we will compare various FPGA data sharing methods. In the previous section, we used FPGA FIFO methods to get number of elements and clear the FIFO. By the end of this module, you will be able to compare various FPGA data sharing methods. Okay, so now that we're at the end of this lesson, let's compare some of the data sharing methods that we've talked about. Let's say we have some data and we need to share it between multiple loops or multiple VIs on your FPGA. So the first thing you want to think about is, do you need to only share the latest data, or do you need to transfer buffered values from one loop to the other or from one VI to the other? So let's say you only need to share the latest data. For example, maybe you just need to share the value of a terminate control or some terminate data. So if we only need to share latest data, then you can use the variable method. So we see here on the list there's variables, so you can use local variables or global variables, or you can use a memory item, or you can use a register item. So you notice that in the lossy column, all of those are lossy because they're only sharing the latest data. Okay. Let's say, however, that you need to actually share all the buffered data. So you want to make sure every value that was written gets read on the receiving side. In that case, you want to use FIFOs. Okay, so we see that on the different FIFO implementations, those are not lossy, right? So with the FIFOs, remember there's three types of implementations. There's the flip-flop one, the lookup table, or the block memory. And you choose the implementation based on how big your FIFO is. So we see that for FIFOs less than 100 bytes, you want to use flip-flops. From 100 to 300 bytes, you want to use a lookup table. And for FIFOs greater than 300 bytes, you probably want to use a memory implementation. So here, this chart kind of wraps things together, shows us the FPGA resources that are used for each method, and we see our common use as well. So this is a good summary for all the subjects that we talked about in this particular lesson.